yeah, in terms of like how it works, because yeah, well, not some of theories. How things work at some atomic particle during the X-ray interactions.
Okay.
Remember I discussed about the 5 different types of scatter radiations? Classical, Compton, for electric, cap reduction, and for disintegration. So we're going to talk about each of these. Starting with the classical, which is the weakest type of scatter radiation, to the strongest type of scatter radiation, which is for the disintegrations. Generally, the weaker type of scatter radiation, the weak energy, interact with the whole atom. As energy gets stronger, it interacts with the nucleus, from the whole atom down to the nucleus of the atom. Talk about the original beam, and that's how it actually creates the photodisintegration. From weak energy, primary beam, interact with the whole atom, that makes classical, to a high energy beam, which interacts straight to the nucleus. Okay, classical scatter radiation. This is interaction between, as mentioned, between low energy X-ray beam, that's a primary beam, and whole atoms. Classical scatter radiation generally occurs when the setting is about below or around 10 keV setting energy. With classical scatter radiations, there's really no energy loss between the original beam and scatter radiation beam because of such a low energy level. The extra photon comes in, interrupt the film, have the same energy as the scatter radiations. Generally, remember the scatter radiation is much weaker than the original beam. But in this case, because the beam is so weak, it's just going to produce the same amount of scatter radiation with the same energy level. So the wavelength then of the original beam, incident beam, is the same as.
Okay, so that's what that means right there, then, right?
Hmm?
That's what that means right there. The last statement is that
Yeah.
they don't change really.
Yeah. So there really no, because there's really no energy.
It's already low as it is.
Yeah. So the original beam have the same amount as the scatter beam energy. So wavelength of the original beam is the same as the scatter radiation. So low energy here, meaning what kind of wavelength it has?
Long.
Long wavelength. With classical, since the energy is relatively weak, it doesn't really have energy to ionize anything. So there's no ionization occur when there's interactions with the classical radiation. Other names for classical that are been used, coherent is one of the most common names instead of using classical. Relay, unmodified radiation, scatter radiation, and then Thomson scatter radiations. I don't know why they have so many different names for this one. Just gonna research it, but those are different names that are used for the same thing. Maybe it was discovered by different people at the same time. I don't know. So here's an animations of classical coming in, yay, and coming out, woo! Same wavelength. All right, content or modify, that's another name. Scatter radiations. Now this interactions between moderate energy, X-ray, and the atoms. Since the energy is much higher, the interaction occur at the outer shell of the electron. Whereas classical, the energy weak, it occurs with the whole entire atom, interaction with the whole atom. This occurs, the interaction at the outer shell. With these interactions, the energy absorbed from the outer shell of the atom will have too much energy and will escape from that atom. So there's ionizations in this process. That's the photon. And when it escapes, it produces scatter radiation, and the photons, the scatter radiation, can direct in any direction, going whatever direction it goes, depending on where it goes.
With classical, it goes in the same direction. It doesn't change direction, or
Costco, yeah, could go any version too. But
Okay.
with photon, this Tecon, it actually could go back to original
Oh.
source. So it was what I call backscatter. So the photon of scatter can actually go back to the original source. What I want you guys to remember with this is that with Compton or modified scatter radiation, it is responsible for a vast majority of radiations reaching the image receptor, which causes unwanted radiographic fog density. And also, vast contribute to mostly to occupational exposure, to the radiographer, to the X-ray tank. Compton is responsible for a vast majority of our exposure. Just images. Compton is going to originally go through patient infected film or other anatomy, then could come out as scatter in the form of Compton. Here we use the same time. But let's you protect us from scatter radiation. Sometimes we have to be in a room with the patient due to fluoroscopy exposure. So patient is the #1 source of scatter Compton radiations. So as we work with our patient in the fluoroscopy room, the patient is killing us. And for Compton's is main response for increasing fog, which is a term used to give us unwanted density or contrast on X-ray film. So by giving too much fog, it gives lower contrast, which gives more unwanted shades of gray and more density, which we don't need.
Doesn't the ionization chamber like fight against that?
Ionization chamber?
Yeah.
That's also dependent. Yeah, that's true. But then, no, because after it interacts with the patient, it produces those scatter radiation. The ion chamber just make the image better in terms of how the setting is.
But it stops the exposure when it's reaching exposure, like limit, right?
Yeah, it does, but the scatter radiation doesn't stop that.
Okay.
It stops the primary.
Yeah, I think basically it's like no matter what, there's always going to be scatter radiation, like no matter what.
Alright, so here's a Compton. That's fine. I mean, not that many electrons, and then here's Compton.
So it only knocks it out while going in, it doesn't do,
It's going to interact with the outer shell.
Mhm.
The outer shell absorbs those energy, have too much energy, then it escape. When it escape, as it escape, it reduces energy from the scatter.
okay.
For electric, sometimes called for electric effect, scatter radiation. This is where the original beam is completely absorbed, and it's absorbed mainly at the inner shell of the atom during the interaction. So from Costco, the interaction is whole atom. Compton interaction with the outer shell. As the energy gets stronger, it then gets closer to the nucleus. So here, it interacts with the inner shell of the electrons. The inner shell will absorb the energy. As it has that energy, it then the electrons can escape the binding energy of that shell. As it's escaped, it then produces scatter radiation in the form of photoelectric. And remember, I talked about how if the inner shell electrons removed, what happened?
Right.
Other electrons will move in. As it moves, it will also produce more scatter radiation. So photoelectric is a type of what?
Is it
Characteristic
characteristic?
radiation, right? In form of secondary scatter radiation.
So the only difference between those two is that characteristic is in the primary.
Yeah, and then this is also produced in produce scattering. But this is form of characteristic in secondary scatter radiation. In general, with high atomic number of such matter element, it will usually produce more photoelectric absorption or more photoelectric scatter radiation. With Compton scatter radiation, the technologists get most of the radiation. In photoelectric, the patients get most of this. Patient receive more photoelectric effect in this type of scatter radiation. Animation photoelectric, go in, interact in the shells, not gravity. Pair production is pair production scatter radiation or secondary radiations occur at usually a setting of 1.2 mega electron volts or higher. Because it occurs with 1.2 mega electron volt, pair production usually does not occur in diagnostic X-ray. It usually occurs in the radiation therapy X-ray because it uses in the mega volt. In diagnostic X-ray, we only use up to what? kV. With pair productions, the high energy come very close to the nucleus, so it go beyond the inner shells, but it come interact very close to the nucleus. Not next to the nucleus, but close to the nucleus. As it interacts close to the nucleus, it begins to lose energy. This losing of energy then produces two types of electrostatic charges. One is for negatrons and one is for positron. In regular physics class, it normally refers matter and antimatter. But in this class, we call it negatron and positron. I don't know why. And of course, in MFI, negatron means negative charge and positron is positive charge. And these two type of charges interact. The negatron actually absorbs very fast to the atoms. The positron then interact with the other electrons. During this interaction, both the positron and the electron combine, and then they eliminate each other. As they eliminate each other out, it then produces two types of photons, each having half the value of the setting, which is 1.02. So it has given two photons, acceleration called, which is about 0.51 mega electron volt each. So it's how separation works. And then that's the two photons. And then we have photon disintegration. Occur when the energy setting, the primary beam, is about 10 mega electron volt or higher. And again, since in the mega electron volt, it's only occur mainly in radiation therapy instead of diagnostic X-rays. The high beam, because of the high energy, the wavelength is very small. This more allow the very smallness of this beam of the wavelength allowed to go straight directly to the nucleus of the atom. In this case, could be the tissue atom. As the beam interacts with the nucleus will absorb all those energy. This causes the nucleus to be in excitation mode. So it's vibrating really fast. As that source, it then breaks down, and then it disintegrates and collapse and explode, and that's how we die.
You said this happens in radiation therapy, right?
Yeah. Mainly because it's in the negative direction. Right, so here we go for this integration. Begins from here, interact the nucleus, and then there goes us. Fun stuff, isn't it?
It's not funny.
So things to remember. This one is what happened.
Mhm.
So with classical coherent, it's not that important because it's so weak. But in terms of other types of scatteration, Compton and Folate, these are the two main things that occur in the diagnostic X-rays. Compton, we receive them as a technologist. For electric, mainly the patients. Type reduction and for disintegration, being the fact is that energy beam is much higher than diagnostic, it's usually occur at the therapeutic procedures. And then technical factor to consider. KB determines what type of interaction occurs. Having high KB usually decrease for electric absorption because most of this go through the patient, so more penetration and less body interactions. However, it so then produces a lot of competent interactions after you go through the patient interact film. Low KB increases for the electric absorptions, so more of the KB will be absorbed by the patients, so increasing patient dose. And sometimes we have no control what KB we have to set because it's based on the anatomy that we have to shoot. So select KB based on type of exam, chest, ribs, or X-ray, and desire of their penetrations and the film contrast we needed. And again, sometimes we have no control of how high or low KB setting we have because of the anatomy that we shoot. So sometimes the patient have to absorb them or we absorb them. I think that's the last slide.
Mhm.
All right, time's up. It's 6:30, come back at 6:45.